Hello, Geometry. Today we're going to be talking about properties of radicals. Now, we reviewed this a little bit yesterday, and you may have seen it even prior to yesterday, but remember that we talked about this symbol in Desmos. This is what we call a square root symbol. And what we know about square roots is that sometimes there's something underneath, like a number. I'll call it x. This actually has a name that I didn't mention yesterday. This is what they call the radicand. And this is a square root because the value right here is left empty. Now, if you were talking about something like a cube root, you would see a number 3 right there in that position. That position is what we call the index. But since it's a square root, technically the index is a 2, but when the index is a 2, meaning it's a square root, we don't write the number there. And what a square root means is you're looking for the number on the radical. What do you square to make that number? So for example, we know 4 squared creates the perfect square 16, and therefore, if I take the square root of 16, I get 4. And what that tells us is it tells us that squaring and square rooting are what we call inverse operations. So squaring and square roots are inverse, or you can call them opposite operations. They undo each other, very similar to adding and subtracting and multiplying and dividing when solving equations. Okay, so we're going to talk about what we call simplifying a radical. So we're going to simplify each radical. Again, we don't want any decimal answers. We want exact answers. So we want our radicals to be in simplified radical form. So look at our first example. I have the square root of 54. Okay. Now, there's a couple different ways that you can do the square root of 54. One way we mentioned yesterday is to think about the perfect squares. Remember the perfect square list we had yesterday. If you need to refer to that or write it down to help you remember it, go ahead. I'm just writing down the first 10 over here off to the side. So you can think about what square root goes into 54. If you know your multiplication facts really well, you'll recognize that the square root of 54 is the same as the square root of 9 times 6. 9 being a perfect square number. Okay. Now 6 is not a perfect square, so I'm just going to leave it. Okay. But I do know that 9 is a perfect square. I'm going to circle that. 9 is a perfect square, and I know the square root of 9 is 3. So I'm going to make a little note right here. Any numbers that are able to come out of the radical because you have perfect squares go out to the front of the radical in the next step. I'm going to put the 3 there, write your radical symbol, and then write the number that's left behind. Now I know that 6 is 3 times 2, but neither of those factors is a perfect square, so this is as far as you can go with the problem. Another way that you can approach simplifying radicals, if you cannot quite put a pin in the idea of what square root goes into 54. Remember, you can also use that multiplication chart. That can also be really helpful. You can Google multiplication chart as well. You can always do a prime factorization. Now remember, a prime factorization is when we take a number like 54 and we break it down into prime numbers. Okay, so maybe you don't know that 9 goes into 54, but you do know it's an even number, so you know 2 goes into it, and 2 goes into 54 27 times. 2 is prime. I like to circle my prime numbers. Tells me to stop. And then 27 breaks down to 3 times 9, 3 is a prime number. Now maybe you stop here because you recognize a perfect square number, or maybe not, and you just keep breaking it down to prime numbers. So what that allows you then to do is to rewrite 54 as 2 times 3 times 3 times 3. And you can see that technically that is 6 times 9, right? So, and then what you're looking for is you're looking for perfect squares. Now 2 or 3 or 3 or 3, none of those are perfect squares. But if I take 3 times 3, that will create a perfect square, 9, and I know that the square root of 9 is 3. So I like to circle the things that are being taken out of the radical. Some people like to cross them out, but anything that's coming out, I put it up here at the top as a mental note to myself that as I go to the next step, that's going to be brought out to the front. I can see that there's only 2 times 3 underneath, and that never will make a perfect square. So I write my square root symbol and I put the 6. And again, that is our final answer. So either method works. Personally, I go back and forth. Sometimes I do it using perfect squares, and sometimes I use it prime factorization, or maybe a combination. All right, so I have 2 examples here that I want you to try on your own. So what I'm going to have you do is pause this video, and you are going to go ahead and try these problems out. Okay, so you can see here in number 2, I got the answer of 2 square root of 6. The way that I chose to do this problem is I broke down 24 to 4 times 6. 4 is a perfect square, and 6 only breaks down to 3 times 2. So I was able to take the square root of 4 and leave the 3 times 2 behind inside. Number 3, I broke down 108 the whole way down to all prime numbers. You may have stopped when you noticed the 9 there, but then again, it's sort of up to you how you approach this. So I took all my prime numbers, which I circle, and I write them in order, all my 2's and then my 3's, and I can see that 2 times 2 is 4, and I know the square root of 4 is 2. 3 times 3 is 9, and I know the square root of 9 is 3. These numbers that are left, that come out, making little mental notes here, what you do with them is you just multiply them together and you put them out in front. Anything that's left behind is written underneath. So like I said, I like to circle everything or cross things out that are coming out so that it's really easy to tell what's left behind. So your final answer for number 3 is 6 square root of 3. Radicals can be multiplied. So if you have the square root of A times the square root of B, that can be the square root of the product AB. So if you have the, the square root of 3 times the square root of 2, that would simply be the square root of 6. If you had something like 2 square root of 5 times 4 square root of 2, you would just multiply the coefficients, the numbers in front, keep the square root symbol, and then multiply the numbers underneath. So 5 times 2 is 10. So you can definitely multiply radicals if needed. Dividing radicals. So when we're dividing radicals, for example, if we have the square root of 3/4. Actually, let me backtrack. Let's do the square root of A over B. That can always be broken up into the square root of A over the square root of B and vice versa. So for example, if I have the square root of 3/4, that's equivalent to the square root of the numerator over the square root of the denominator. Now the square root of 3 is a prime number, so you can't take the square root of 3, but I do know that the square root of 4 is 2. So that allows you to simplify it by using this, this property. If you have 6 square root of 3 over, say, 2. So if you have something like this, you would be able to simplify the numbers that are outside the radical to give you 3 square root of 3. If you had something like 6 square root of 10 over 2, you would only be able to reduce the numbers that are outside the radical. You cannot reduce a number inside the radical with a number outside the radical. So this, again, simplifying this would become 3 square root of 10. So this is a little bit of information about dividing radicals. And the last thing that we want to talk about is this concept that when you have a simplified radicals, there are no radicals allowed in the denominator of a simplified answer. So for example, if you have the square root of 3 over 2, and you're like, oh, let me break that up to the square root of 3 over the square root of 2, I can see here that I have a square root underneath the radical, and this is not allowed if it's simplified. Okay, so because it's what we call an irrational value in the denominator, so we want that to be rational. We want that to be a number that is not a square root. So what we are going to do is we're going to do what's called rationalize the denominator. It's kind of a long name, but that's what they call it. And this process is the process of eliminating the square root in the denominator. Okay, so I'm going to show you how to do this on just a couple of examples. So if you had something like, let's do, you got to your final answer and it was like 3 square root of 2. Okay, so if you had 3 over the square root of 2, you cannot have the square root of 2 in the denominator, and you can't divide 3 and 2 because this isn't a 2 in the denominator, it's a square root of 2. So what we're going to do is what we call rationalizing. Now, rationalizing is the idea of making this radical not be there anymore. Well, one way we can get rid of a radical, if I have a radical, I just need to multiply it by itself. And what that will create is a number underneath the radical that's a perfect square. So in order to rationalize the denominator, we just multiply the denominator by itself. So we multiply the denominator, I'm going to abbreviate that, by itself. Okay, so I'm going to multiply that by the square root of 2. Now with a fraction, just like if you were finding common denominators, whatever you multiply to the bottom, you must also multiply to the top. So when I go to then simplify this further, okay, I get 3 times the square root of 2. Now 3 is a whole number, square root of 2 is a radical. You cannot multiply, it does not become the square root of 6. It does not become 6. What it becomes is 3 times the square root of 2. So you just write it side by side. Sort of like if you were doing 2 times x, you would write 2x. Now square root of 2 and square root of 2, those are both radicals. You can multiply radicals to radicals and what I like to call numbers to numbers. So this is radical times radical, which is the square root of 4. Okay. Now, oftentimes this step that I'm writing right here, I often sort of skip this step and I go straight to what you're going to see in my next step. So I have this 3 square root of 2, and I know in the denominator I have square root of 2 times square root of 2. Square root of 2 times square root of 2 is square root of 4, which I know is 2. Now this is your final answer. You cannot reduce this 2 with this 2. That is not allowed because this is a number and this is a square root. Okay, we're going to do one more. I'm going to show you one more example and you'll get a chance to practice this. So if I have the square root of 5 thirds, I know that that is the square root of 5 over the square root of 3. You cannot do anything with square root of 5, but you can definitely do something with that square root of 3 because you don't want it to be there. So what you're going to do is you're going to multiply that denominator by itself. And with fractions, whatever you do to the denominator, you must do to the numerator to keep it equivalent. So I can go ahead then and I can multiply my numerators. Notice that they're both square roots. And the multiplication of radicals says that you can multiply any square root to any other square root to give you the square root of 15. And then square root of 3 times square root of 3. The purpose of doing that is because I know it's going to make a perfect square of 9 underneath the radical, which gives me a value of 3. So remember, these two together give me square root of 9, which I know is 3. So I sort of do that part in my head. Now I cannot simplify the 15 and the 3 because this is not a 15, it is the square root of 15, which is technically a decimal value. So since those cannot be simplified, this is your rationalized answer. Okay, so I hope you enjoy this video and best of luck with your practice.